Hello, this is John Noguera of SigmaXL. Welcome to our webinar. Today we're going to talk about what's new in DiscoverSim version 2. And we'll do a few case studies to illustrate the use of the new features that are in DiscoverSim version 2. And before I launch into the new features of DiscoverSim, I just want to give a little bit of background in terms of what DiscoverSim is. And then we'll take it from there and look at the new features that have been added. So first of all, it's an Excel add-in for Monte Carlo simulation and optimization. So if you have uncertainty and you'd like to model that uncertainty, then this is the tool for you. Monte Carlo simulation allows you to quantify your risk, and then optimization can be used to minimize your risk. DiscoverSim uses easy to understand language. For example, we use outputs and inputs. It's ideal for design for Six Sigma, risk, and project management. It's very powerful. There are a lot of distributions, 53 continuous distributions, 10 discrete distributions. We have automatic best fit, and you can specify correlations between your inputs. It's also quite fast. We have an Excel spreadsheet interpreter that accelerates the calculations in the background. I'll talk a little bit more about the technical details of that. You can do sensitivity analysis, identifying your important X's. Global optimization, we'll talk about some of the new methods that we've added to global optimization. And the optimization is stochastic, so that you can not only, for example, maximize the mean, but minimize the variation, maximize a process capability index. And also, DiscoverSim is bundled with SigmaXL for statistical and graphical analysis. In DiscoverSim, you have quite an array of options for metrics to optimize. And this is just a list. I'm not going to go through them in detail, but just to show you that there are lots of different metrics that you can choose, whether it's to minimize or to maximize. You can pick off whatever particular metric is of interest and run the optimizer. We also have a desirability function. Desirability function is useful in a multiple response optimization problem, so more than one output. And also we have minimize mean squared error, which is another useful one, Taguchi loss function. So if you have a target, it incorporates a penalty for deviation from target. And lots of different distributions. Pretty well most of the major distributions that are available. There are a few esoteric ones that are not on this list, but if it's unimodal and continuous, then there's a really good chance that you're going to find a distribution that will work. The most common ones are normal, triangular, and uniform. Normal distribution, because of central limit theorem, a lot of data is normally distributed, and so you can use that. If you are uncertain and you have no data, but you do have some group knowledge in terms of worst case, best case, and most likely, a triangular is a good one. Uniform is a good one if you want to be conservative in your simulations and equal probability over the entire range. Pearson family is useful if you, for example, with non-normal data, and you just plug in the mean, standard deviation, skewness, and kurtosis. There are also custom distributions that give you added flexibility, and we'll look at a few different examples with the distributions. Certainly we're not going to cover all of the possible distributions, but the distribution fit tool works with all of these distributions and rank sorts in Anderson-Darling from smallest to largest to tell you which distribution is the best fit. Now, just a little background, the components of DiscoverSim. First of all, it is an Excel add-in, but it is much more than an Excel add-in. There is an interface, which is the Excel spreadsheet interpreter, and then in the background we use what is called the Gauss engine, which is popular amongst econometricians. It's a very powerful matrix language, matrix programming language that allows us to do calculations that are much faster than would be available in Excel or in Visual Basic for Excel. Also, we have a very good random number generator, and we also have, for global optimization, MIDACO-SOLVER, and I'll talk about that in just a little bit. DiscoverSim is $995, which is quite competitive. It includes simulation, optimization, the Excel interpreter, distribution fitting, and SigmaXL statistics. It's also a perpetual license, and we have discounts for academic and volume. So now let's talk about version 2. The first thing that we're really very excited about is the MIDACO-SOLVER. And this was developed in collaboration with the European Space Agency to do interplanetary trajectories. This is actually an artist's rendering of the Mercury mission, Mercury probe, that there is an actual contest for these interplanetary trajectories, and MIDACO holds the benchmark world record for the solution, the best solution for solving very difficult optimization problem, these interplanetary trajectories. So it's a very strong solver, particularly with mixed, discrete, continuous, and constrained. So essentially what we're saying is that if MIDACO is good enough to solve interplanetary trajectory problems, it's going to be good enough to solve the most difficult of business problems. I've already mentioned that we have the Monte Carlo simulation with the 53 continuous and 10 discrete distributions. And what's new now is that in version 1, we did not, the only thing you could do with the distributions was to specify the distribution for Monte Carlo simulation, and now we've added the ability to do non-normal process capability. So for Six Sigma practitioners, that gives you a much larger selection of distributions to work with if you have non-normal data. We've also added some other optimizers. Nelder-Mead is very useful. It's a local optimizer. It's very fast. And if you have non-smooth, so for example, if you have a clip or an absolute value function, so it's not a quadratic response, a smooth response, then Nelder-Mead handles that quite well. Also, for small discrete problems, exhaustive discrete has been added. And there are cases where really the best solution is to try all possible combinations. And if the problem is not that large, then that's really what you want to do. So we've added the exhaustive discrete, and it will automatically, in hybrid mode, it will actually attempt, in the case where all the control factors are discrete, it will try all the combinations. And it will also run a test to see if it's going to take too long to solve it. And then if it takes too long, it'll move on to other methods. The genetic algorithm we had in version 1, and we've improved the constraint handling in the genetic algorithm. So also a hybrid, because now we have 5 different methods, and the hybrid kind of takes care of utilizing which optimizer when, depending on the type of controls that you have, whether they are discrete or continuous or a mixture. So as I mentioned, also the non-normal process capability for all 53 continuous, and you can even do capability on the discrete distributions. Just some additional technical notes. Anderson-Darling p-values are available for all of the distributions. We did extensive Monte Carlo simulations, 50,000 runs per, to come up with the ability to compute the Anderson-Darling p-values, and that's something that normally there are published tables, but those published tables are for just a select group of continuous distributions. This way, we have Anderson-Darling p-values for all of the 53 distributions. Custom distributions in version 1, we had weighted, and now we've added unweighted. It's just a convenience factor. If everything is equally weighted, you can just use the unweighted custom distribution. Also, a stochastic information packet If you have standard library of data and probabilitymanagement.org, talk more about the SIP standard, Stochastic Information Packet. So we support that on an input basis. We don't provide the standard report format, but we do allow you to specify a standard library, and if you want to include that as one of your inputs in your simulation, you can do that now. We've added a step size. Previously in version 1 you were limited to integer increments, and now you can specify a different value. Also very useful is the insert DSIM function. So now you can add intermediate calculations and then perform and then add those to constraints, and I'll be illustrating that. So that adds a lot of flexibility over what you could do in version 1. We've added a percentile statistic, and then under correlations, previously all the correlations were, the initial correlation matrix between all the inputs was 0. And there are cases where you may want to specify a correlation and then relax the other correlations. You don't really care what the other ones are, so you can actually essentially set those to blank, and that makes it easier to find conditions that satisfy the specified correlations of interest. So what I'll do now is I'll illustrate the new process capability. So I'm going to open up practice data, and in this feature is in SigmaXL, but SigmaXL only has about 16 distributions. So now what we'll do is I'll do distribution fitting with the customer data, with a batch distribution fit, use entire data table, and we'll go to overall stat. So overall satisfaction is customer satisfaction on a scale of 1 to 5. We want to analyze this data, continuous data. Now, I should briefly talk about a threshold. A threshold is a shift in the data. And to solve an optimal threshold, it does take considerable computation power when you have 53 distributions, and a number of those actually are candidates for threshold distributions. So to speed up the process, the default is to exclude threshold distributions. So in other words, it will not try to apply a shift to the data. If you have negative values, however, that will be overridden, and automatically it will search for an optimum threshold. So let's just go ahead and run this. So this is the batch distribution fit, which is the first step of the process. This function was in version 1 and gives us a tabular output sorted in Anderson-Darling from order from smallest to largest. And now notice that for every distribution there is an Anderson-Darling p-value. The beta distribution clearly is the best fit, and you can use this in a Monte Carlo simulation scenario. What's new in version 2 is now you can go ahead and run a process capability. So with this distribution on the fitted data, I have a lower spec limit of 3.5, so a customer SAT score of less than 3.5 is considered a defect. And I can actually use either a z-score method or a percentile method. The z-score method is desirable. It has better properties, and that's I won't get into the details of that now, but it allows you to compute not just long-term capability indices, PPK, but it also allows you to compute CPK, because you're normalizing the data. And then once it's normalized, you can apply either regular standard deviation or moving range methods. Whereas the ISO, the percentile method, only allows you to produce regular or long-term capability indices. So let me go ahead and run that. And we can see from the histogram So this is new in version 1. You weren't able to actually get the distribution fit on the data. And this gives you the prob plot, the beta prob plot, as well as the beta curve fit on the histogram. And here's the lower spec limit. Clearly, this is a process that is in need of improvement. We predict 33% less than the lower spec limit. So this would be an example where it would be something that we'd want to improve this process. I just wanted to illustrate the use of the new capability, the process capability on the 53 distribution. So I could have picked any of the distributions. I just picked the best fit one. And that's typically what you would do. Unless you happen to know for theoretical reasons that one particular, like a Weibull distribution, is the appropriate theoretical distribution, then you would, in that case, you would select the Weibull distribution. Okay, so let me go back now to the PowerPoint slide, and I want to now talk about MIDACO. MIDACO stands for Mixed Integer Distributed Ant Colony Optimization, and I'm not going to get into the technical details, but at a high level, it is essentially modeling the way ants forage for food. And that proves to be actually a very effective way to have a random component, but also some limited memory in terms of finding the best solution in a complex global optimization problem. And there's, like I said, there's a fair bit of technical information. The website MIDACO-SOLVER.com provides numerous technical papers. We have licensed this technology, and if anybody is interested, Dr. Martin Schluter makes available benchmark studies and lots of technical information on Solver. So as I mentioned, it was developed in collaboration with the European Space Agencies, and it holds the benchmark world record for the Messenger probe, which was the mission to Mercury. And this is considered the most difficult space trajectory problem in the European Space Agency Global Trajectory Optimization Database. That's like a competition, and they provide the code. Anybody can actually compete and submit a solution. So currently, MIDACO is the record holder. So this is the actual website, and there's our posting here. MIDACO gets embedded at SigmaXL. This is the European Space Agency website with information on the benchmark messenger. And as I mentioned, this is something that really any team can submit. You can download the problem code and attempt to solve the problem. Our GA, genetic algorithm, is another evolutionary algorithm, and really the key point here is that we've improved it to handle, to be stronger at handling constraints using MIDACO's constraint handling penalty method, called the Oracle penalty method. I mentioned the discrete exhaustive optimization, and the discrete exhaustive optimization, the key thing here is that clearly in a combinatoric problem, it's only going to work for fairly small problems. So what we do is we run 50 trials, compute the average time per run, and then compute the total number of combinations, and then if the amount of time required to solve exceeds the specified, in this case 2 minutes is the specified, you can increase that. But if the estimated time to do the total combinations exceeds that limit, then essentially the optimization is stopped. And if you're in hybrid mode, it'll just go on to a different method. Practically, if you have a binary problem with, say, 13 or 14 variables, discrete exhaustive works very well, and we'll illustrate that in just a bit. Sequential quadratic programming, that was in there in version 1. We've made some improvements to the algorithm, and Nelder-Mead has been added for non-smooth local problems. And the Oracle penalty method has also been added to the Nelder-Mead optimization. Hybrid ties it all together, makes it easy to use. If you have all continuous controls, then it's going to use a combination of MIDACO, GA, and then one of the local optimizers, depending on whether it's smooth or non-smooth. If you have a mixed continuous discrete, it will use two different settings on MIDACO, followed by the local optimizer. And in the all discrete case, it'll start with exhaustive if applicable, but if then it kicks in with MIDACO. Let's go now to some case studies. So the first case study is an example from Dr. Harry Shaw on Six Sigma project selection. We have a variety of different projects, improvement projects, that we want to work on. We have a requirement that the sum total of the savings of the projects is $1 million. Each project has different resource allocation requirements and risk of, or likelihood of success. This is also all in the workbook that comes with DiscoverSim. Switch over here. Now, in order to save time for the webinar, I have set up the model, and what we have here are projects A, B, C through to I. So a total of 9 potential projects, and we want to pick the projects to maximize expected savings. However, we don't have a lot of data, but we do have a pretty good idea in terms of what the minimum expected savings would be, what the maximum expected savings would be, and the most likely. So this is a good example where triangular distribution comes into play. Okay, so each project, the team estimates the best case, the minimum expected savings, the maximum expected savings, and the most likely. Then, for each project, a probability of success is assigned. Again, it's somewhat subjective, but based on the team's experience with varying degrees of project complexity, a probability of success is assigned. Notice project E has an expected most likely savings of $2 million. These are in thousands, so, but it only has a 50% chance of success. Also, for each project, we have the resource allocations, number of people that need to be assigned to the project. And notice that project E requires 10 people. What we have are controls, also known as decision variables. And the controls, in this case, are binary, 0, 1. So 0 means this project will not be done, 1 means the project will be done. And with this right now, I have them all set to 0. So what I'm going to do is I'm going to change to select all of the projects, and then I will run the simulation. So basically, I'm running the simulation, and I'm going to put in a fixed seed value just so that the results match what's in the workbook. And ordinarily, you would just leave it to the system clock, which means that every time you run it, you'll get a slightly different result. Accelerated mode is the mode that uses the Excel spreadsheet interpreter. You can add sensitivity analyses and so on and so forth. And we'll run this. And here's our simulated output, 10,000 replications. There's our lower spec limit management requirement of $1 million, 1,000 times 1,000. And you can see a lot of variation. The mean savings of $3 million, but the standard deviation of 1.1 million. So very large standard deviation. So the risk of failure is 1%, failure being defined as a savings of less than $1 million. However, the big problem is that the total resources, all we did was we just brute forced it, selected all the projects, But we have a requirement here that we are limited in the budget to 20 people. So this is an unacceptable solution. So I'm going to go back to set this thing to all zeros. And now I'm going to run the optimizer. And I should mention here, this is what I've done is I've, in addition to the controls, a constraint has been added. So the constraint specifies that the total resources must be less than or equal to 20. So now I'll run optimization. And in the optimization, I'm going to maximize the mean because there are replications. So we're maximizing the mean. And I'm going to use the hybrid. And we'll just go ahead and run that. Okay, so that was really quick because it used the discrete exhaustive. There are actually only 9 projects, so very quick to try all possible combinations. So these are the projects that were selected. And I'll now go in here and we'll go ahead and we'll run the simulation now with these projects that have been selected. So now we satisfy the constraint of 20 resources. And compared to before where we were expecting $3 million in savings, now it's $2 million in savings, but the standard deviation is still quite large. Essentially it's almost $1.1 million standard deviation, so lots of variation and a lot of risk because as you can see here on the empirical performance, there's a 19.5% chance of failing to meet the minimum management requirement of $1 million in savings. What I want to do now is I want to rerun the optimizer, but instead of maximizing the mean, what I'm going to do is I'm going to maximize the process capability. And there are different process capability indices. I only have a single spec, a lower spec, so I'm going to run PPL. Let's go ahead and run the simulation and see what we get. So I pasted the results in, and now the expected savings are 1.9 million, but notice the standard deviation has dropped dramatically because previously we said let's maximize the mean. Now we said let's maximize the process capability. And in the process capability index, you're doing 2 things. You're maximizing the mean and you're minimizing the standard deviation. The expected failure or defect rate is now only 3%. So this is actually a much better outcome. The savings aren't quite as high, basically 2.0 versus 1.9, but notice how much of a difference in the standard dev. We basically went from a 1.1 million down to half a million, or 0.49 on the standard deviation. So that is really a dramatic reduction in the variation. And if you look at what happened, basically this project E, which was the high-risk project, was eliminated. So the one that had only the 50% chance of success, this was the one that was actually causing the uncertainty. Now, it may well be that this is an important project and something that needs to be done, but in terms of allowing you to play out the different scenarios and giving you options, you now have the tools to make better decisions. And so in this case, the recommendation is that you not do Project E. Now, what I just did with maximizing the process capability, I want to show you another way of doing it, which utilizes the new feature, the insert DSIM function. I'm going to now add this new DSIM function. This DSIM function, what it will do is every run in an optimization, it will compute the particular statistic of interest. So essentially all of the optimization statistics are available, and the one that I want to use here is the DSIM standard deviation. And I want to do a standard deviation of the output. So what I've done here is I've created the function DSIM standard dev. I could have typed this in, but I'm just using the dialog. So this is what it will do. The DSIM standard deviation is that during the optimization, it will compute the standard deviation at the end of every Monte Carlo simulation run. But now, what we can do is we can add that to the constraint. So we'll create a new constraint, and on the left-hand side is going to be the DSIM function, and I'm going to say I want the standard deviation to be less than 500. All right? So what I'm showing you are two different ways of getting the same outcome. Last time we maximized the process capability index. Now I'm going to maximize the mean subject to this additional constraint. So again, maximize the mean. We'll run this. Everything else is the same. Again, it's very fast because it's discrete exhaustive. And you'll notice that, again, Project E was not selected. We accept this selection, rerun the simulation, and the results are the same as maximizing PTO. Okay, so the DSIM function gives you lots of flexibility. Essentially, any of those statistics can be used in intermediate calculations and applied on the left-hand side of the constraint. So that concludes the first case study. The next case study that I want to look at is an engineering example. This is from the Catapult problem. When we optimize a process capability, how is it that you can actually maximize the mean and simultaneously reduce variation? If you have a response that is a nonlinear response, often there are settings in the control factors where the transmitted variation can be dramatically reduced. So here in the Catapult with a launch angle of 30 degrees, you see quite a large transmitted variation, whereas if you shift the launch angle, you get to a sweet spot where there is a very small amount of transmitted variation. And that's the essence of design for Six Sigma, robust design. And what the optimizer is doing is it's finding those sweet spots in the response where you are minimizing the transmitted variation. So it's looking for maximizing the mean, but it's also looking to reduce the variation. So now I want to look at the spring force. And this, by the way, this is from Andrew Sleeper, his book, Design for Six Sigma Statistics, and is used with permission. So this is a solenoid gas shutoff valve, and what we're trying to optimize is the spring force. If the spring force is too great, the shutoff valve will not open when necessary. If the spring force is insufficient, then it will be stuck open. So it's critical that the correct spring force be established. And so that's what we're going to look at now with this engineering problem. And in this worksheet, what I have I'm using uniform distributions. So it's a very conservative tolerance optimization problem where you're allowing an equal probability over the entire specification range. We can actually control the nominal. And what I'm doing is I'm now setting a control with a minimum and a maximum. And basically, this control is what the optimizer is going to work on to try to find the solution that maximizes the process capability or whatever metric we specify. So what I'm going to do to start with is I'm going to run the simulation just so we kind of have a baseline condition. So this is the initial condition, the before improvement. And as you can see, there's a lot of variation. We can do sensitivity studies and so on and so forth, and then identify which factors are the greatest contributor to the variability. But in the interest of time, what I want to do is just focus on the optimization of the control factors. So what we're going to do now is allow DiscoverSim to play with the settings of the nominal. Essentially, you're just moving that nominal, kind of like the pullback angle of the catapult, subject to some constraints that are necessary for tolerancing purposes. We are going to now look for a solution that improves our likelihood of meeting the spring force requirement, which is between 20 and 24 newtons. So lower spec limit of 20, upper spec limit of 24 newtons, and a target of 22. I will now run the optimizer. And in this case, I'm going to use hybrid. These are all continuous inputs, so it's going to use MIDACO. And I can set the system defaults. One of the things I want to do to just speed up is limit the maximum number of iterations to 100, just to expedite the process. I want to just do 1,000 replications. And what I want to do in this case is I'm going to maximize the CPM. Now, CPM is a process capability index that kind of similar to the Taguchi metric in that it incorporates a penalty for deviation from target. So we're going to maximize the CPM. A good process capability index is 2 from a Six Sigma perspective. Minimum acceptable process capability is 1. You can think of process capability as like the size of your garage. If you have a double-car garage, it's no problem to park your car in the garage. If you have a single-car garage, you have to be really careful not to veer too much to the left or the right, otherwise you're scratching your car or actually you're hitting your mirrors. So we want this process capability index to be 2 or higher, ideally. And again, I'm going to set the clock or the seed value just for replication purposes so that the results are consistent with the workbook. And so I'm going to go ahead and run this now. And MIDACO starts, and it has already found a process capability index of 6.6. That is a huge improvement. And that was just in a matter of seconds. In fact, to speed up the process here, I'm just going to hit interrupt, and that'll kick in the genetic algorithm. And the genetic algorithm isn't really going to find an improvement over MIDACO. Sometimes it does, so that's why it's incorporated in the hybrid. And the last thing we do is a sequential quadratic. So there's our final solution, a CPM of 6.6. I will paste the results in, and we'll run the simulation, and voila, we have a much improved design thanks to the powerful optimization, finding that sweet spot to minimize the transmitted variation. Okay, so with that, we'll call it a wrap, and thank you all very much for your participation.